Okay, the first part of the class is very heavily devoted to measurements. In chemistry, and physics, we have very specific ways that things need to be measured, much more specific than you see usually in anything up until now. It's critically important that we know how to take measurements. And so that's really going to be our focus for right now. And so why do we begin with that? First of all, because when you're in lab, you're constantly taking measurements. If you're doing a chemical reaction and you're making some new chemical, it's really important that you know how much of it you got. Just like if you're cooking, right? If you're making any kind of a dish, be it cookies or some kind of a chicken dish or anything like that, you need to know how much ingredients you have that are going into that. So that's all measurements. And so chemistry is just filled with measurements. We need to be able to look at them intelligently and say, does this answer make sense? Or does this answer seem a little bit strange or a little bit odd? And so we start with this right from the beginning. And as I mentioned, I find that most people who take this class for the first time aren't really aware of how strict we are with measurements in chemistry. This class is extremely detail-oriented, very, very detail-oriented. And I think this chapter kind of really makes it clear how much focus we put on details. If I ask you a question, you rarely just answer with a number. It's usually a number with some kind of a unit that tells us that we have a measurement involved. All right, so for example here. Oops, lost all of you here. And still no problem seeing the screen, right? No issues? Okay. Sorry, it's just whenever I change anything, I want to make sure everybody can see this. If there's ever a time where you all are having a hard time seeing things, please stop me and let me know. I'll be more than happy to adjust to that. Okay. To the best that I can. So if I ask you, how far is it from Rio Hondo College to UCLA? Your answer always has to have two pieces of information when we're saying how far. A number, and then some kind of a unit to give us the context of the number. So for example, someone could say, all right, it's about 25 miles by driving distance, or you could give me a distance in kilometers. You could give me a distance in inches, but that wouldn't really make much sense, but you could do it. And in California, of course, we often measure in terms of time. How long would it take you to get there? But usually, of course, how far means we would want distances. But the most important thing that you need to understand there is that there is a number and there is a unit. What we're going to find out is that numbers and units work a lot like numbers and variables in algebra. So when someone says 25 miles, miles is a lot like a variable would be in algebra, X or Y, something like that. It's going to work the same way. There are many kinds of things that we measure, but the ones that we're going to measure the most in this class, we'll start off with length because it's the most familiar. It's not the one we use a lot in chemistry, but just it's something that's easy for us to measure and to practice with, which is the distance from one location to another. So we have many different possible things that we could measure for the distance from the center of one atom to one it's attached to through bonds, or the distance from one star in the galaxy to another star. So there's all kinds of different lengths we can measure at all kinds of different scales. Mass. Mass is probably the most important of all the measurements in chemistry, but unfortunately, it's the most confusing. And mass is telling us how much matter there is in something. The more matter something contains, the greater its mass. Now, the problem with that definition is, of course, that it uses the word matter, which we haven't really defined. And what matter is will become more clear as we go a little bit further. But matter is essentially going to be pretty much everything out there that's made up of our fundamental particles, which are called what in chemistry? Our fundamental particles starts with an A.
Atoms.
Atoms, exactly. So atoms, and then the subatomic particles that make those up, the protons, the neutrons, the electrons. We'll see all those guys coming up shortly in the next chapter. But for right now, we'll just say that mass is just a measure of how many of those things there are on a scale that we can easily deal with. The English language introduces a confusion, and that is when we're talking about mass, we often talk about weight and mass interchangeably, and they are technically different things. When someone technically uses the word weight, how much something weighs, they're actually talking about forces. When we talk about something's weight, we all know that it's being held to the earth by what force? We call that force?
Gravity.
Gravity. Excellent. Good. So gravity is holding something down. And the extent of that force is what we call the weight. So it's the attraction between whatever you're weighing and the earth or the moon or Jupiter or wherever you're there. So weight isn't the same thing as mass. Weight depends on the context. Now, do you agree that it's unlikely we're going to be weighing anything on this class on the moon, or we're going to be weighing anything on Jupiter? Probably not going to happen. In fact, I can guarantee you, not going to happen. So usually when we're talking about weighing things, we're always talking about the Earth here. So if we're talking about a 1-ton rock on the Earth, its weight would change if we moved it to the moon. How much does something weigh on the moon compared to the Earth? More, less, or the same?
Less.
Less. And when you take physics, you understand the reason for that. It's because the moon has less mass. So things weigh less on the moon than they do on Earth, less mass than the Earth. What about on Jupiter? If you could weigh something on Jupiter, which would be a real feat, it would weigh more, much heavier. Yeah, because Jupiter is much more massive than the Earth. So again, that's attraction between the Earth or the planet that you're on and whatever you're weighing. Mass is the amount of matter that it has in it. So if I take that rock and I move it from the Earth to the moon, it still has the same number of atoms in it. It's still the same composition. So does its mass change? Turns out, no. Okay. Mass doesn't depend on where you're weighing anything. The reason I bring this up is because why is this a problem in English? Because when we want the mass of something, what do we almost always tell someone to do? We tell them to go and weigh it, right? We don't tell them go mass this. It's just not a word we use. We say go weigh this. And fortunately, the balances that we use in chemistry all tell you the mass. They adjust the weight to give it to you as a mass. So we'll look at the different values between these, but for right now, even though these are technically different things, we'll treat them as interchangeable in our class. All right, there are 3 really big things I want to try to get through today. The first thing should be a review, and that's scientific notation. Can I get show of hands if you know how to digitally do this, by the way? I don't know if you all know how to do this, but there should be, you all have something that looks like this in your Zoom, right? Correct? There should be a way to do reactions. Where's your reactions?
Oh, yeah.
Yeah, you can all react, like hands up, hands down, that kind of a thing here. How many of you have seen or used scientific notation at one point in time? Yeah, it looks like a lot of you. So this should be a review. But even if it is a review, don't go walking away. Don't run away and go, oh, I'm going to go somewhere else. We're going to use scientific notation a lot in this class. So it's important that you know how to do it and what is considered proper scientific notation, the correct way, and what is not proper scientific notation. Scientific notation is an alternative way of representing numbers, and it is largely used when you are using numbers that are very large and very small. It's used to avoid having to do what when you're looking at numbers? When you're looking at a number, what do you not want to have to do? You don't want to have to count
zeros.
Yeah. So if there's a long decimal number, you don't want to have to count 0.00000. Oh, that's just miserable. Scientific notation makes that so much easier. The same thing with really large numbers. Okay, so that's why we have it here. So how many atoms are there in a glass of water? It's a huge number, vastly huge number. And so scientific notation would answer that. What's the distance between two atoms in a sugar molecule in meters? Very, very small number. So we would need to use scientific notation to answer that. Okay. And so it really simplifies working with numbers that are very large, very small. Okay, so I'm going to switch to my notes for right now. Oops. Hold on one second. Okay, so you all see my notes packet, right? Again, this is on the website. You can download this. I'm using an awesome program called Drawboard, which I love using, but apparently is a real pain when students try to submit homework using it. I don't know why, but it doesn't seem to really work very good for submitting homework, but it's really great for lecturing. So I love using it for this. So you see everything that I've been talking about, all those slides. You know, if you're going, oh my God, he's going so fast, I have no idea what he's writing down. All those, everything that's on those slides is here in my notes. Okay. Everything that we talked about, it's there. So this next part is probably easier to just do using my notes. All right, so how do we do this? The way we do this is scientific notation. In proper scientific notation, we always take the decimal and you move the decimal so that it's between the first and second non-zero number, or let me be more specific, after the first non-zero digit. So here's a number, 582. We don't need scientific notation for it. That's not too big of a number. But let's say we did want scientific notation. We know that the decimal is technically hiding right there. Yes? Even if we don't write it?
Yeah.
So we move the decimal until it's after the first number that's not zero, which would be the 5. Note how many places you moved it and also which direction you go. So I go 1 to the left, 2 to the left. Now you agree 582 and 5.82, are they equal or not equal?
Not equal.
Yeah, they're definitely not equal. So that's only the first step. Whenever you move the decimal to the left, what are you doing? That's really important. Every time you move the decimal to the left, you're making a number 10 times larger or smaller?
Larger?
When you move the decimal to the left, you're
Smaller.
always making it 10 times
Smaller.
Smaller.
good. And if you move it to the left twice, that's 10 times 10, 100 times smaller. So do we agree that 5.82 is 100 times smaller than 582?
Yeah.
Yes.
Yeah. So these are not equal. So the way we balance out moving the decimal is we now need to say, well, this is 5.82 times 100. But we write it as so. Every time you move to the left, we say that's a power of 10. So if you move to the left twice, 5.82, you move to the left twice, that would be 5.82 times 10 to the second. Let me do another one. Let's say we had 5,137. We know the decimal is hiding here. So I would have to move the decimal 1, 2, 3 places to the left. So in scientific notation, this would be 5.137 times 10 to the
Third power.
third power. Good. Every time you move the decimal to the left, that's correct. That's how you do it. What about this number here? 0.0024. Here we need to move the decimal to the
Right.
Yeah, it has to be after the first number that's not 0. So 1, 2, 3. But moving the decimal to the right makes the number 10 times
Bigger.
greater. Good. So clearly these aren't the same. I have to multiply it by something smaller. So instead of going by a power of 10 that's larger, it goes by a power of 10 that's smaller. So every time you move the decimal to the right, you go down by 1. So this would be -1, -2,
-3.
Very good. 2.4 times 10 to the -3. Okay.
So to the left is greater and to the right is smaller.
Yes. Yeah,
Okay.
it always does that. That's always how that's going to work. Now, I want to point out one other thing here. So let's say we've got 2.4 times 10 to the -3. Let me move it down a bit. Do you agree that I could move the decimal to the right one more time? That would be 24 times 10 to the -4. These two are equal. But what's technically the difference? The difference is the one on the right is what I call proper scientific notation. That's how you're supposed to do it. Because the decimal is after the first number to the after the first number that's not 0. This is not proper scientific notation right here. It's technically called exponential notation. It's okay for intermediate calculations. Meaning on the way to an answer, but your final answers should never be like this. They should always be in proper scientific notation. Sometimes I will use these numbers, and I'll show you when we look at them, but not for final answers. When do we use scientific notation? Often it's a judgment call. First of all, if on an exam I specifically say, use scientific notation, you have to use scientific notation. But a lot of the time, it's just a matter of, does it look like it makes sense or does it not make sense? Usually what I say on exams is to use scientific notation in the following contexts. I'll say, number 1, numbers greater than . 10,000. Or numbers smaller than. Zero point zero zero one, 1,000. But that's all just a preference. That's my preference. If you go to Chem 130, your professor might have a different set of guidelines. The key is this: don't make me count a whole bunch of zeros. That's usually all that I ask. If I have to count 10 zeros, I'm really unhappy. I can count 2 zeros. I can count several zeros on this end, but anything beyond that, don't do. Commas are only used for visual, making things simple. Commas have no meaning, though, in scientific notation and should be ignored. All right, so could you please write these numbers in scientific notation? These values here in scientific notation, and don't round any numbers. Okay, so write these in scientific notation. And I'll give you just a second to do that. Oh, by the way, if you want to put answers in the chat, please do it just to me if it's an answer to something instead of to everyone. Thank you. Okay, let's go ahead and take a look and see what we got here. So on this first one, the decimal had to be moved 1, 2, 3, 4 places to the left. So 2.3894. And if you're moving the decimal to the left, the power of 10 goes up. So 1, 2, 3, 4, up to 4, 10 to the 4. It's a positive number. In this case, question? We have 4.289 times 10 to the minus 3. The decimal had to be moved 3 to the right. And then the same thing was true here. Decimal had to be moved 3 places to the right. Question about, is this lab time? Not yet. I don't believe so. Let me double check. We go from 9:40 to 11:10 or 11:15. So we're still in lecture time. Okay, let me double check on that. But yeah, we're still going until, I will usually go till 11:15. Okay. All right, so I have a question for you. So for right now, please do not use the chat room. And for right now, I'm actually going to turn off the chat temporarily. I am going to put a polling question up. Okay, so you all see this here.
Yeah.
What I'd like to know is, what is the value of X? And I'm going to put up a poll right here. So decide what the answer is. Don't say it. Don't type it. Decide what the answer is, A, B, C, or D. And give me an answer, please, to what the actual value of X should be there. If it's 3, 4, -3, or -4, what should X be? Okay, about 5 more seconds. And I do keep records of these to see who's participating. So please make sure you're participating. All right, and I'm going to go ahead and end the poll right now. Good. And so you can all see the results right now, correct?
Yes.
The correct answer was, in fact, D. Okay, it's not majority rule. Can you see my arrow moving on the screen right now?
Yes.
Yeah.
Okay, yeah.
Yes.
Yeah, good. So it is -4 because I had to move the decimal 1, 2, 3, 4 to the right. And when you move it to the right, it's going in the negative direction. So X would go from 0, -1, -2, -3, -4. Okay. Let's do another one. Okay, which of these is not correctly paired? So did they not write the correct number in scientific notation? And I'm going to go ahead and put the poll up. And here we go. Wow, I'm impressed. Almost everybody's getting this right. Okay, so 2 more seconds. 3, 2, 1. Good. Okay, the correct answer on this one is C. C is not done correctly. If they move the decimal 1 to the left, it would be 0.760 times 10 to the 1 or whatever, but they didn't move the decimal at all. If you don't move the decimal at all, what would the power of 10 be? You don't move the decimal at all, it'd be 0. Okay. 7.60 times 10 to the 1 is 76. That's 76. So this is good. Very important. What is 10 to the 0? What is any number to the 0 power except for 0 itself? The answer is not 0, by the way. Any
Just
number
one.
to the 0 power is 1. Very good. So 10 to the 0 is 1. 7 to the 0 is 1. 0.85 to the 0 is 1. Any number to the 0 power is 1. Good. So, but 10 to the 1 is 10. 7.6 times 10 is 76. Good, good. So about 75% of you got that right. Let's try one more. Okay. So which of these is not written in proper scientific notation? So those are all valid, but one of them is not proper scientific notation, the way it should be written. About 10 more seconds. Okay, I would remind you. Oops, is the poll still up? Oh, it looks like it got lost. Shoot.
No, it's not up anymore.
Sorry. Is it up now still?
Mm-mm.
Okay, well, 41 out of 42 of you answered anyway. So, okay. A lot of people did not get this one right. You're all seeing the results right now?
Yes.
Yeah, we see it.
Yeah,
Yeah.
and in this case, the correct answer is, in fact, the one that most people picked. It's D. What's wrong with D?
The decimal place.
Yeah, the decimal, remember, needs to be after the first number that's not 0. All of these are okay because the decimal is after the first number that's not 0. 4.25, 6.0, 3 point. So this should have been 1.54 times 10 to the 4th to be correct. Decimal needs to be right there. Remember, if we go back to the notes, that's what we said with proper scientific notation. Decimal needs to be right there. If the decimal is not after the first non-zero digit, it's not proper scientific notation. Okay, so that's good. It's a good starting point. Now, the next big thing that we're going to be looking at is measurements. Now, in every measurement that we take, with a few exceptions that we'll talk about a little bit later, the measurements are said to have digits that are certain and some, or one that is uncertain. Whenever you take a measurement, this is an absolute rule, which is why I'm going to even highlight it in yellow. You always determine the digits that you know without question, that you're certain of, and then you estimate exactly one uncertain digit. Okay, and so we're going to see that in just a second. A quick reminder, because I'm going to be using these terms a lot. You should have learned these all, I don't know, when did you learn these? The place values years and years ago, right?
Yeah.
You use these terms a ton, a lot. If you've forgotten them, you need to make sure you have them memorized. So the 1 is in the thousands place, this 2 is in the hundreds place, etc. Make sure you don't confuse hundredths place, which is the 6, with hundreds place, which is the 2. Okay. So I'll use these words a lot in this class: 10,000ths place, thousands place, tenths place. We're going to need this to understand these digits as we move on further. Okay, so how do we estimate digits, and how is this going to work? I'm going to swing over to my PowerPoint for just a second here. All right, so let's say you're taking a measurement using a ruler that has tenths as its smallest marking. What that means is you will see space between those markings, correct? You'll have, say, 2/10 of a centimeter, 3/10 of a centimeter, but you will see open space in between there. And so your measurement needs to estimate in between the tenths, which means that you always are going to go 1 decimal place to the right of the smallest markings. Always, always. I'm going to say this sentence, I would say 1,000, that's not true. Probably about 90 something times. And that's not an exaggeration. You always measure 1 decimal place to the right of whatever the smallest marking is. So the smallest markings are tenths. You would give your answer. What's to the right of the tenths? The hundredths. Without exception, you would give your answer to the hundredths. And you'll see a demonstration of this in a second. If you're using a thermometer that has whole digits, in other words, the ones place as its smallest marking, you would always give your answer to what decimal place? What's 1 to the right of the ones place? The tenths place. And we call that last digit the uncertain digit, or the uncertain or the estimated digit. Let's take a quick look at an example of this. Okay, do you see that the thermometers are different in the way that they're structured here? If we look very, very closely at the thermometer on the left, look at the smallest markings. This is 32, this is 33, but in between, what is this line right here? Right above the 32 is 32.
0.10.
0.1, good, 32.10 or 32.1, 32.2, 32.3. What am I counting by? 32.1, 32.2, 32.3. I'm counting by tenths, right? Those are tenths. The answer should always go to the hundredths, because I should be able to read right in between the tenths here. I know that this is more than 32.3, but I know it's less than 32.4. So I estimate. Looks like it's a little closer to 32.3 than 32.4. So 32.33. So these first 3 digits are called the certain digit. The last digit is the uncertain one, or the estimated digit. If I look at this thermometer, notice I don't try to take the measurement first. Forget about taking the measurement. Look at the scale first. This is 30, this is 40. So what does this line stand for right above 30? This line is
31.
31, and then that line is
32.
32, 33. I'm counting by what? 30, 31, 32, 33. I'm counting by
Once.
Ones.
1. So my answer must go to the 10th. Good, because I can see here that this is more than 32, but less than 33. So I estimate in between 32 and 33, 32.3. These these thermometers would probably cost a vastly different amount of money. The one on the left would be more expensive. It's giving you more certainty in your measurement. It's giving you more precision in your measurement. This one lets you go all the way to the hundredths place. The one on the right is not as good. It only lets you go to the tenths place. But remember, it's always one decimal place to the right of whatever the diagram is. I'm going to go to 1115 real quick. On an electronic measuring device, like you see here, you always write down all the digits, but is there uncertainty? Sure, there's always uncertainty. The uncertain digit is always the last one. It is the 5 in this case. So the 6, the 8, the 6, the 0 are certain. The 5 is uncertain. In this diagram, you'll see here that this water is making a curve. Anyone know what we call that curve?
The meniscus.
Meniscus, good. And whenever you're using a solution that's made up of water, which is pretty much everything, the meniscus always goes down. So we always read at the bottom of the meniscus. That rule is hard and fast. You always read at the bottom of the meniscus. The only exception, which we will never use anymore, is mercury, because mercury, the meniscus goes up. With mercury, you read actually at the top of the meniscus. But that's never going to be an issue for us. So for us, we will always read at the bottom of the meniscus because we're not going to deal with mercury. Okay, so if I ask you what's the measurement, don't ever start with a number. Start by looking at the lines. This line is 60, right? This line is 70. So what are all these lines in between? If this is 60, what is this line I'm showing right now?
61.
61, that one is
62.
good. So I'm counting by ones, 60, 61, 62. So when I use this device, I will always go to the what decimal place?
To the 10th
To
place.
the tenths. Good. One beyond the ones place. The tenths. So what would be a good measurement here? Let's say that where my ruler, this is the bottom of the meniscus right here. So what would be a good measurement right there?
68.
But that's not going to the tenths place.
68.2.
I would say 68.2 is an excellent good. If someone said 68.3, would you be angry or upset with them? Or would you say maybe? You'd say,
Oh,
sure,
it's possible.
it's possible. That's definitely possible. How about 68.1? Probably. That's probably okay also. I probably wouldn't agree with 68.0 because it's not on the line. It's definitely above the line, right? But 68.1, 68.2, 68.3, you see, the point is we are uncertain about that last digit. We are just doing our best to estimate it. Okay. So always one uncertain digit.
Could I ask you a little bit to clarify the I know you guys said it was 68.3. How did you guys get the 3 again?
Because what I did here is number one, I'm estimating. So I'm not sure. That's the first thing. But if this is 68, you agree that that line is 68 right there?
Correct, yes.
And that's 69 right up there that you can barely see.
Right,
The curve is closer to 68 than 69, right?
right.
So it's going to be less than half. So
Oh, okay.
68.2, 68.3, if that makes sense.
Yeah, it does, it does.
But I'm not certain. There's no way I can be certain.
So that's why you guys call it remember the uncertain
Uncertain digit. Yeah.
Okay, yeah.
Uncertain or estimated, because you're making your best guess.
Got it. Thank you.
Yeah. And I know I'm running a little over today, but no one has a class other than my class right after this, correct? I don't think you can. Well, there might be a way to have a PE class right after. But could you all please practice here? I'd like you to do your best to figure out the length of the red line and the blue line in each of these pictures. And then we'll finish with that today. And in the notes, this is all in the notes, so it should be easier to see in the notes. They're bigger in the notes. So those are the first two. By the way, no one should be leaving this class and going to the lab right now. That would make no sense because I'm still here. The blue lines are the ones I'm really worried about, by the way. Those are the ones you're going to make mistakes on. Okay, let's do that red line first. Before you ever even try to take a measurement, what do? You look at the markings. So what does each of these smallest markings stand for? Ones, tenths, hundredths? What do those lines stand for?
Tenths.
They're tenths. Very good. That's 4, that's 5. So this is 4.1, 4.2, 4.3. So you agree on the red line, we are certain that it is between 4.2 and 4.3, yes?
Yes.
Yeah.
Yeah, we're certain of
Yes.
that. But we must go to the hundredths. Remember, if the smallest markings are tenths, you go to the hundredths. So we're uncertain about the next one. I'm going to guess 4.24. And the unit is what here? The unit is
Centimeter.
centimeters. Do most of you agree?
Yes.
If you
Yeah.
said
Yes.
4.23, is 4.23 okay?
Yes.
Sure.
Yes.
4.25?
Yes.
Sure. 4.39?
No.
No. Has to be 4.2 something. And probably the closer to the halfway point, the better. Now, this is where people mess up. And this is what I will be largely asking on the exam, is this one right here. Let's say that's right on the line. If that's right on the line, how should you write that?
3.00.
Excellent. Why 3.00 if it's right on the line?
Because it has tenths places, so you need to add one more number after that to the hundred.
even though it's right on the line, absolutely. Even if it's right on the line, you always go to the hundredths place if the smallest marking is the tenths place. Can you agree these next two rulers? These are the same rulers, except what? The only difference between these rulers and these lines is that this one I left these little lines out, right?
Mm-hmm.
So that means you're going to have more certainty or less certainty about your measurement.
Less.
Yeah, you can't be as certain. And are you allowed to do this, by the way? Do you think you're allowed to go? No, you're not allowed to do that, okay? If it's not there, it's not there. So you just have to do the best with what you're given. So doing the best with what you're given, we can agree what are the smallest markings? 0, 1, 2, 3. The smallest markings are what decimal place?
10.
And
These right here are ones, right?
Oh, those, yeah.
So you can only go to the
Tenths place.
tens. Very good. Excellent. So it's going to be between 4 and 5. It's closer to 4 than 5. So what would you say?
0.2.
4.2 would be a good answer. And unit would be centimeter.
Centimeter.
And then what about this one if it's right on the line?
3.00.
3.0.
No, just 3.0.
3.0.
Okay. So then what is the difference between 3.00? These things mean something different to me. What do they mean to me? This one means that I used a ruler that had more precision. It had more markings. I'm more sure about the 3.00, correct? I have less uncertainty. This one, the way we usually read this is, this could be plus or minus 1 of whatever. So this could be somewhere between 2.9 and 3.1. That's what that's telling me. It's telling me somewhere between 2.9 to 3.1. Because remember, I'm not sure of the last digit. But this one is telling me 2.99 to 3.01. I have a lot more certainty about this measurement because I've got all these extra little lines to help me than I am about this one. All right. Now, you'll never see a ruler that's like this these days. You'll almost always see them like this. All right. Good. And if you wanted even more certainty than this, you'd need really specialized equipment, like something with a laser that can measure that. We'll pick up next on Thursday. We'll finish this off by looking at some more of these drawings. So I practice and practice and practice and practice this because we're going to be, the whole first lab is literally just practicing this kind of stuff. Because if you have to take measurements correctly, or else you can't do chemistry. If you're always writing down the wrong measurements, you're always going to get the wrong results. So we spend a lot of time for the first couple of weeks in lab making sure that we can write down the measurements correctly.